Okay, we're going to start recording now. This is AP Calculus, Chapter 1, Section 2. It's the second assignment from Section 2, so 2B, Relations, Functions, and the Graphs. This is how I'll name them all year long. We're going to work on a few more functions today, especially absolute value functions. So let's take a look at our first example. Here's a standard absolute value function you've seen many times. The idea with this, though, is that you must be able to break down absolute value functions into their piecewise format. That's where the majority of the points will be awarded. So on this type of problem, what I'm going to expect you to do is, first of all, determine what value of x is the most interesting value of x in this problem. And that is x equals -3, because it causes the argument to equal 0. So we're going to get two different functions. One function to the right of -3 and a different function to the left of -3. So you have to break it up into two pieces. So we're going to look first when x is less than -3, and then we're going to look at when x is greater than or equal to -3. When x is less than -3, if we plug a number like -4 into this absolute value problem, we'll get a negative sign inside the absolute value bars. And in order to make a negative become positive, we negate it. So every number that's less than -3 is going to produce a number inside the bars that's negative. And in order to make it positive, we have to negate what's inside. So we're going to eliminate the absolute value bars and negate what's inside the absolute value bars for that section of this function, that piece. So if I distribute the negative sign, I get y equals -x minus 3. Over here, when x is greater than or equal to -3, the absolute value bars are meaningless because the number is already positive or 0. So we can just eliminate the absolute value bars and write y equals x plus 3. Now, we write this in proper piecewise function format, which is f of x equals, or you could write y equals is fine. You have a big brace, one big brace, not two. You always work from left to right. If it's not written left to right, I will take points off. The left part of this function is defined when x is less than -3. There's the domain restriction for this part of this piecewise function. And the function is defined by this -x plus 3. So here it is. It's this piece of the function, and it is for this domain. Likewise, the second part of this piecewise function is this function, x plus 3, and it's defined for this piece of the domain when x is greater than or equal to -3. It really doesn't matter if you have the negative sign on the top piece or the equal to sign on the top piece or the bottom piece, as long as it is in one and only one. It cannot be both, otherwise it's not a function. But you have to be used to writing these correctly in piecewise format. They're going to ask you to do this a bunch on a variety of problems throughout calculus. Let's graph this now. I know we're not supposed to plug -3 into this first piece, but we need to plug it in to know where we start. If we plug in -3, okay, if we plug in -3, we get out negative of -3 is +3, plus 3 is 6, okay? I'm sorry, that might create a problem here. Let's take a look at this. It's defined to be -x minus 3. Sorry about that. When I look at this over here, I wrote it down wrong. -x minus 3. When we plug in -3, negative of -3 is +3, minus 3 is 0. Go back 1, 2, 3, up or down 0 is that point right there. Right now, it's technically an open circle. So I probably should do this because it's not defined at that point. But we can plug in numbers less than -3, like -4, and get out 1, -5, get out 2. And we're going to get this line right here. There it is. But now we've got to graph the second piece of this piecewise function. And if we plug in -3, we still get out 0. It fills in that hole. It always will on these types of problems. And then we're going up 1 to the right 1, up 1 to the right 1, and that's how we get the second piece of that function. There it is. There's a graph of it. The domain is right here. It's already listed. Yeah, it's all real numbers. You can plug any number into this. There is no domain restriction in terms of the overall function. You could list the range. The range is greater than or equal to 0. The range of this function. Y is a set of all real numbers such that y is greater than or equal to 0. You could write it in interval notation. Bracket 0, comma, positive infinity. Okay. There is an x-intercept. The x-intercept is at negative 3, 0. The y-intercept we see is at the point 0, 3. Okay, there are no asymptotes. There's a nice picture of this. Many of you could have done the graph without breaking it down. Understand, this will be the majority of the points on the test because we do not have a rule for handling absolute value functions in calculus. We must break them down into their piecewise format. Let's take a look at another one. You will see this function again several times. The graph of this or something very similar to this is on the Chapter 1 test. I'm just going to be honest with you. It's on there because it's going to come up again in Chapter 2. It's a great problem when you are talking about limits. In Chapter 2, we're going to talk about limits. And we want to do the same thing. The breaking point is always whatever makes the argument inside the absolute value bars 0. And in this case, it is simply 0. So we need to look. When x is less than 0, this function is going to act totally different than when x is greater than or equal to 0. The equal to sign you could put at either spot. I always like to put it with the positive portion. But it really wouldn't make a difference. It wouldn't be incorrect if you did it the other way. So when x is less than 0, if I pick a number like negative 1, that's less than 0, and I plug it into this function, I get a negative sign inside the absolute value bars. That's a problem. I have to make a negative become positive. How do you make a negative become positive? It's not magical. We have to negate it. Negate a negative to make it positive. So if I'm looking at numbers less than 0, I have to negate whatever is inside the absolute value bars. So I'm going to negate it. It's negative x over x. And negative x over x reduces to be negative 1. There it is. Where if x is greater than or equal to 0, I can leave the absolute value bars alone. And I just get x over x. The absolute value bars just go away. The number's already positive. We don't have to do anything to what's inside. And we get y equals positive 1. How can that be? Well, it can be because this function just jumps from negative 1 to positive 1. If I were to graph this, first of all, one thing that is incorrect about what I have down is I shouldn't even have an equal to on this right here because of the fact that 0 will make the denominator equal 0. So I have to restrict that from the domain here anyways. So if we write this piecewise function, here's what it's going to look like. Always write the piecewise function from left to right. Here it is. This is the left part of this function is this blue part right here. When x is less than 0, the y value is always negative 1. So the function equals negative 1 when x is less than 0. The red part is the right-hand side. That comes second. It equals positive 1 when x is greater than 0. Okay? That's what we're going to end up graphing. I'll put this in red so you can see where it comes from so it matches up, and then I'll match up the graph with that. Alrighty? Here's how this is going to look. When x is less than 0, we will always have negative 1. It's a horizontal line. When x is greater than 0, we always get positive 1. There it is. There's what that function looks like. It's an interesting function. It's not defined at 0. It's a step. There is a domain restriction. If you were to list the domain in this problem, the domain of this function would be x is any real number such that x cannot be 0. And therefore, if we wrote this in interval notation, it would look like negative infinity to 0 in union with 0 to positive infinity. Interesting, that's how it works. The only thing that's being excluded is the number 0 by writing it this way. The range of this function is kind of interesting. Here's how we would write it. In interval notation, it really looks, or in set builder notation, is actually a bit easier because y is any real number such that y equals plus or minus 1. That's it. That's all it can equal. It's either 1 or negative 1. Done. To do it in set builder notation is kind of problematic in order to do it. Okay? So it's definitely much better using the set builder notation. So we'll just do it that way on this particular problem. X-intercept, there's no x-intercept, there's no y-intercept, so that would be it. This is a nice function. You're definitely going to see it again in chapter 2. Okay, let's move on to the next example. Very similar to the last example. Have these absolute value bars that we need to deal with. Again, the breaking point is at 0 because 0 makes the argument of the absolute value portion 0. That's just x. What do I get if I plugged in what number for x would it make what's inside the absolute value bar 0? And if I plug 0 in, the argument of the absolute value would equal 0. So we're going to look at when x is less than 0, and this time we can look at when x is greater than or equal to 0. Because now it can equal 0. 0 will not make the denominator equal 0 like it did in the last problem. Okay, so let's take a look at this first. I always set it up left to right. When x is less than 0, if I pick a number like negative 1 and I plug it into this problem, I get a negative sign inside the absolute value bars. That's a problem. In order to make a negative become positive, you have to negate what's inside. So be careful because here's what it's going to look like. X minus negative x all over 2. And minus a negative becomes plus a positive. And x plus x is 2x. When I divide by 2, I get x. When x is less than or equal to 0, or when x is greater than or equal to 0, the number's already positive. Just leave it alone. So we get x minus x over 2. And that is 0 over 2, which is 0. That's it. If we write this in its piecewise format, here's what it's going to look like. F of x or y equals, I just like using functional notation whenever I write a piecewise function. I'm going to say equals x when x is less than 0, and it equals 0 when x is greater than or equal to 0. Can this be? And the answer is yes. If we plug 0 in to the top piece, even though we're not supposed to, because right now it's an open circle, we get 0 out. If we plug in negative 1, we get negative 1 out. Negative 2, we get negative 2 out. Negative 3, we get negative 3 out. There it is. If we plug in 0 into the bottom one, because that's where we're supposed to plug it in, it fills in this hole. So it is what we're going to learn. This is called a continuous function. It is a nice continuous function. But it doesn't V back out like a normal absolute value would. It does this. Again, I put this one on the test, and many students miss it because of the second piece here, because it rides right along the x-axis. And if you just use your graphing calculator, it's hidden behavior. You won't see it graph along that x-axis. So I like to put things where there's hidden behavior on the graphing calculator. Again, graphing calculator proficient, but not graphing calculator dependent. You have to know that the graphing calculator is graphing that portion of the graph. The domain here is all real numbers. I'm not even going to write it down. The range would be all numbers greater than or equal to 0. So the range in this particular problem, y is the element of all real numbers such that y is greater than or equal to 0, which is bracket 0 because it's inclusive, comma, positive infinity. The domain, if we did want to write it, the domain is negative infinity to positive infinity, or you could just say x is the element of all real numbers if we use set builder notation. And it's domain, not range. Okay. X-intercepts, it has multiple x-intercepts. It has x-intercepts at every point where x is greater than or equal to 0. The y-intercept is the point 0, 0. Okay? I'm not necessarily going to list them on problems like this. I usually don't ask when you have something strange like that. Let's take a peek at this. How would we type this in to our graphing calculator? Just so that you have an idea how it's going to work. Okay? If we wanted to type this in, here's what it would look like. We would say y equals, which is this point, this right here. And we're going to type in, it was x, and then we're going to subtract. Hopefully that x comes up here. Okay, x, we're going to subtract the absolute value of x. Okay, the absolute value of x. In order to get the absolute value of x, it is math over to number. Okay, so math, we're going to go over to number, cursor to the right. It's the very first one, so we hit the 1. Okay, there's the absolute value of x. And then we hit x again. Okay, we're going to cursor to the right to get out of there. Now we're going to divide this whole thing by 2. Now, I've got to be careful here. I'll go divide by 2. If I graph this, I won't get the same picture. And the reason is we have to put parentheses around the x and the absolute value of x. So if I cursor backwards here, I'm going to need to insert a left parentheses. So I'm going to go second. Insert is the delete key. Okay? Let me do this again. It'll be right here. I'm going to go second, insert. I'm going to insert a left parentheses. And then I'm going to cursor to the right. And I will insert a right parentheses right here. So again, I'm going to go second, insert, and I'll go right parentheses. Now if I go to the end, I don't even have to go to the end if I didn't want to. Okay? I can hit enter. There it is. And if I hit graph, now if I hit graph, sometimes you don't always get a good picture of it. I'm going to go zoom 4. It's a nice zoom to use, zoom decimal. And here it comes. Okay? There is my picture. Now, notice I didn't see this piece over here to the right. So if we take a look at it, one way to change that is to go back to y equals. And if I cursor backwards, okay, so that I'm over top of this line that's blinking right here, and I hit enter, that will make it more solid. So now when I graph, if I just hit graph, not only do I see that, I can see that it is writing along the x-axis. Okay? So there's a picture of it. Now that we look at this, this doesn't look like the picture I had drawn. So let's go back. Okay? And the reason for that is I drew this piece incorrectly right here. I'd like to say I did that on purpose, but I didn't. I made a mistake. It happens. When you plug in -1, you get out -1. If you plug in -2, you get out -2, and it should go like this. There it is. And then the red piece will fill it in. So it's nice to check things using your graphing calculator to make sure that everything works out correctly, like this problem right here. Okay? So there's a look at that problem, and we got a little bit of the idea of how it's going to work with the graphing calculator as well. Next slide. Example number 5. Just graphing piecewise functions. Every year it seems like piecewise functions give students problems, and I really can tell you why. I mean, in years past I would have said, and I don't know why, but I've really boiled it down to this situation. The problem is students do not plug the breaking point in. In this case, is this 1, when x is less than or equal to 1, or when x is greater than 1. You must plug it into both pieces. And students only want to plug it in the first piece because that's where it says equal to, and then they want to start the second piece at 2. Don't do that. Plug 1 into both pieces. I'm going to plug 1 into the top piece. When I plug 1 into the top piece of this function, when I plug 1 in, I get 2 out. I can't plug 2 in. It's got to be less than or equal to 1. So I'll plug 0 in and get 3 out. Negative 1 and get 4 out. Let's graph it. 0, 3. 1, 2. Okay. Negative 1, 4. It's this line right here. There it is. It's got a y-intercept of 3 and a slope of up one, back 1, up 1, back 1, up 1, back 1, up 1. There it is. Here's the problem. A lot of students, when they're doing piecewise functions, that's the first part of this piecewise function. They want to then start at 2 and they have a big gap in between. Don't do that. Even though it says x has to be greater than or equal to 1. 1.1 is still greater than or equal to 1. We got to graph that point. 1.01 is still greater than or equal, it's still greater than 1. You got to graph that point. So just graph 1. When I put 1 in, I get 2 out. It's going to take off right where this one left off. I don't have to put an open circle around it. I mean, you can if you want, but it's already closed. Just start at that point. And now count out your slope. Up 1 over 2. Up 1 over 2. But do not have a gap between x is 1 and x is 2. You still have to graph all those values between 1 and 2. Don't miss it by not graphing the parts in between. The book will then ask you for various points. F at negative 1. Negative 1 is less than 1, so it's got to go into the top piece. It's 3 minus negative 1, which is 4. F at 0. 0 is less than 1, so it's 3 minus 0, which is 3. F at pi. Pi is greater than 1, so if I plug it in, it is simply 2 pi. Done. Done with that problem. Example number 5. Example number 6. Another piecewise function. Same idea. This says when x is less than 5, the value will always be 1. So when I go back to 5, 1, 2, 3, 4, 5, I go up to 1. It's this point right here. It's an open circle. And when x is less than 5, it will always be 1. There it is. It's that piece right there. When x is greater than or equal to 5, the y value will always be 0. I made a mistake again. Sorry. Might help if I go to the right 5. 1, 2, 3, 4, 5. Up 1. Okay. It's going to look like this. There it is. Okay. When x is greater than or equal to 5, the y value is always 0. There it is. Done. It also wants us to compute a few points. F at 0 is 1 because 0 is less than 5. F at 5. 5 is greater than or equal to 5, so it's got to go into the second piece here. We get out 0. F at 6. 6 is greater than or equal to 5, so we get out 0. There it is. There are the points that they want you to graph. You can ask for x-intercepts, y-intercepts. These are all graphs that you're going to see in Chapter 2. Because Chapter 2, they love piecewise functions when we start talking about limits. Example number 7. Taking another look at another piecewise function. Now we have a parabola. I'll do it in green. Then we're going to have 2 different lines. Again, I know it says x is less than 1 here, but plug 1 into that function. When you plug 1 in, you get out, you go x, f of x. Plug 1 in, you're going to get out 3. Now, if you want to circle this or indicate that that's not really a point, but plug it in. When we go to the right one, we go up 1, 2, 3, and circle that point right there. We may fill it in, or we may not. It depends on if this turns out to be continuous or not. If we plug 0 in, we get out 4. If we plug -1 in, we get out 3. -2, we get out 0. Okay? -2, we get out 0. -3. -3, you get out like -5. Okay? And here it is. It's an upside down parabola. You should recognize it as such. Okay? It's an x squared, which is a parabola, and it's got a negative sign for a lead coefficient, so it's got to be upside down. Now, let's plug 1 in to the second piece. If we plug 1 in here, we get 3/2 plus 3/2, which is 6/2, or 3. It fills in that open circle. It doesn't have to all the time, but it does. It fills in that circle. And now it's going to go up 3 units. 1, 2, 3 over 2. Okay? And there it is. And it's a closed circle from here to here. That's the second piece in blue. And then the third piece in red. Again, we have to plug 3 in to see where we start. 3 plus 3 is 6. So right where we left off at this point, we're going to take off right from here and go up 1 over 1, up 1 over 1. Just the slope changes slightly. This is a continuous function because where we left off at 1 with the green function, the blue function took off right where we left off. And the red piece took off right where the blue piece left off. So it's a nice piecewise function. I could ask you to find the x-intercept, which is right here, the point -2, 0. The y-intercept is the point 0,4. You could list those things. There's no asymptotes. Domain's all real numbers. Range is all real numbers. I'm not going to list all those out, but you could ask for those. This is the last example, and this one tends to give students problems. Either you get it right or you tend to have problems. It's a long problem. I'm not sure if I'm going to be able to fit everything on this screen, but I'm going to give it my best. This may be one that you really have to get down in class, so you should be able to see it twice. I'm hoping I don't have to do this homework problem that's like this one. There is one like this on the test. First of all, we have 3 different breaking points. X equals 0, x equals +1, and x equals +3. Because those are the 3 numbers that will impact when the argument of this function equals 0. So the first interval I will do in black when x is less than 0. And I could do less than or equal to. It really doesn't matter. When x is less than 0, if I pick a number like -1 and I plug it into the first absolute value, I get negative number in there. When I plug it into the second piece, I get a negative number, and I get a negative number. To make those negatives become positives because of the absolute value signs, I have to negate what's inside. So I'm going to negate what's inside the first one. I'm going to negate what's inside the second absolute value, and I'm going to negate what's inside the third one. And if we distribute and collect like terms, we get something that looks like -3x plus 4. That's the first piece of this puzzle. It would be graphed in black. The second piece are the numbers between 0 and 1. When x is greater than or equal to 0, but less than 1. When that happens, let's pick a number like 1/2. If I plug it into the first absolute value, it's already positive. Leave it alone. If I plug 1/2 into the second one, I get 1/2 minus 1, which is -1/2. It's negative. I have to negate what's inside. If I plug -1/2 into the third one, I get a negative, so I have to negate what's inside. Distribute the negative signs, and we get -x plus 4 for the second piece of this puzzle. I will do the third piece in green. That will be when x is less than or equal to 3, but greater than or equal to 1. And maybe I'll leave the equal to off here again. It really doesn't matter as long as you only define 3 in one piece. Never define a number in 2 different parts of a piecewise function. It only can be described once. Otherwise, it makes it not a function. If you pick a number like 2, if I plug 2 into the first one right here, I get a positive out. Just leave it. If I plug 2 into here, I get a positive 1 out. Just leave it. If I plug 2 into here, I get a negative out, so negate what's inside. I get 2x minus 1 minus x plus 3, which is x. 2x minus x is x plus 2. Okay? I get x plus 2 back out. I still have one piece of this puzzle left. I'm going to have to extend the page here a little bit so that I can say what happens when x then is greater than or equal to 3. When x is greater than or equal to 3, if I come back up here, if I plug 4 in, this is positive. That's positive. That's positive. Just leave them all be. It's going to be x plus x minus 1 plus x minus 3. And we get 3x minus 4 out. To write this entire situation in nice piecewise format, here it is. It's 4 different pieces. Make a nice big one. Okay? I'm going to get negative 3x plus 4 when x is less than 0. For the second piece, it's in red. Negative x plus 4 when x is less than 1, greater than or equal to 0. The third piece is in green, which is x plus 2 when x is less than 3, greater than or equal to 1. And the fourth piece is 3x minus 4 when x is greater than or equal to 3. Those are the 4 pieces of this graph. Now let's go graph it. If we plug 0 into this first piece, we're not supposed to, but if we plugged it in, we get 4 out. 1, there it is, starting right here. 1, 2, 3, 4. It's open circle right now. And it's a slope that says go back 3, up, okay, it's rise over 1. Go up 3, back 1. Okay, here it is. There it is. Looks like that. If you plug in 0 into the second piece, it fills in this hole right there. And it's got a slope of down 1 over 1. It's just that short line right there. That's all it is. If we plug 1 into the third piece, we get out a positive 3 as well. It fills in that hole. And now we're supposed to go up 1 over 1 because the slope is 1. Up 1 over 1 for 2 spaces. Up 1 over 1. Up 1 over 1. Here's an open circle for right now. Is it going to get filled in again? If we plug 3 in right here, we get 9 minus 4, which is 5. It fills in that hole. And now the slope is back to positive 3 up 1. There it is. That's what this curve looks like. It's kind of strange, but it's a V-shaped, and it changes 3 times. The one that's going to be in your homework is going to come down, flatten out. It'll look more like this. Flatten out and take off again. You get a nice constant in the middle, and that's the type that I put on the test. The one in the notes is actually harder. Work yourself through the problem. Come back and listen to this and see if you can't figure out when you're negating, when you're not, and get this thing written in proper piecewise function. Most of the points on the test are awarded for writing it in proper piecewise function. Last example, then you'll have the assignment, and we'll be done with section 2 of chapter 1. We're doing a bunch of fog, Goff, those types of problems. Here it is. F of g of x. This should be big time review, but here's some in case you've forgotten. Take x, plug it into the g function. What comes out? X squared minus 3 comes out. Now take this and plug it into the f function. The f function says take whatever comes in and add 5 to it, which will make this x squared plus 2. That's it. Done. What about Goff? G of f of x. Take x, plug it into the f function. This comes out. Now take that and that will be the input. The output of f will be the new input for g. So x plus 5 squared minus 3. Make sure when you multiply this out, do not make an algebra 1 mistake of making this x squared plus 25. You have to be able to multiply this out and get x squared plus 10x plus 25 minus 3. That mistake might happen in algebra 1, should never happen in calculus. That's 22. There it is. Okay? So don't forget to multiply out when you're squaring binomials. F of g of 0. If you take 0 and plug it into the g function right here, 0 minus 3 is negative 3. And now we plug negative 3 into the f function, which says negative 3 plus 5 is 2. Likewise, you could have just plugged 0 in right here, because you've already found the composite, and 0 plus 2 would be 2. So you can either crank out the composite again, or just use your composite function. Likewise for g of f of 0. G of f of 0. Take 0, plug it into the f function, and you get a 5 out. If you take 5 and plug it into the g function, you're going to get 5 squared minus 3, which is 22. Okay? The last couple that it asks for here is g of 2 to find g of 2. We have not found this composite yet. So we take 2, we plug it into the g function. We get 2 squared minus 3, which is 4 minus 3, or 1. That's the output. That becomes the new input coming right back into the g function, which is 1 squared minus 3, which is negative 2. So g of 2 is negative 2. And lastly, f of x. Take x, plug it into the f function. When you plug x in, you get x plus 5 out. Now take that and plug it right back into the f function, which is x plus 5 plus 5, or x plus 10 out when we do f of x. Okay? There it is. Lots of different problems in here. I think the absolute value stuff, getting used to writing that in piecewise notation is huge. So here's the assignment. We will finish going over the notes today, or it'll actually be, it's Sunday right now, so it'll be tomorrow. We'll end up going over that tomorrow, and hopefully get even into some of these notes so you can start working on it. But I'll put this up so that people can start watching these notes right away if you want to come back and look at something. All right? See you in class tomorrow.